idle control is a really important aspect of an engine calibration. So I'm going to explain how each of these calibrations affects the engine and how best to set them up. So first of all, let's go over the different aspects and what they do. So the idle map select method basically allows you to choose between how you can choose between base duty 1 and 2 and target 1 and 2. So for example, at the moment the idle duty select map is on cow switch. So if I was to set my target in here at 1500 for 2 and then my target here for 1 at 700, if I was to open a RPM trace and then choose under calibration switches number 2 to be there, if I jump to then cow 2, you can see the engine RPM jumps up and it will slowly increase the integral in order to maintain the RPM which I'm targeting. Now you can also do it based on gear. So if the car is in neutral or park, it will basically use base bypass duty 1 and target 1, and if it's in drive it will use the 2 tables if you select it based on gear here. This is useful for automatic transmission cars where basically when they put it into drive and the torque converter take up, that the RPM will be pulled down, in which case some more duty will be needed. Air charge temperature base duty adder is pretty simple. As the air density changes, you generally will need to change your idle duty opening. And the aircon base duty adder is basically when the compressor kicks in, it will put extra load onto the engine, in which case you need to actually apply more throttle opening or more bypass duty. This you can actually see being applied here. So if you open your idle base duty, which is your base duty table, and then this is the drive-by-wire target idle output, because we're set the bypass duty to idle at the moment. We'll come back to that. What you will see is that when the aircon turns on, if I just turn it off a sec, your drive-by-wire target idle comes down. When it turns on, we can actually see that the RPM dips really low just for that split second, while the compressor comes in with a real whack on this particular car. So what we can actually do in order to help that, we can change your bypass duty effect. Let's just go wild with it and put it to 1. You can see the drive-by-wire target idle comes up then. And then to see the difference, if we turn it off and then turn it back on, instantly the throttle will jump up and the RPM doesn't dip as much then. So that's a useful function as well. And what you can also do is change your target engine speed based on the aircon switch as well. The bypass duty table and the target tables are based on engine coolant temp and runtime. So for example, if you want to have the RPM target higher when it's colder or once the engine just started, you can do so in this particular table to set your target. Now the bypass duty effect, this basically applies to how you've got your idle duty, your idle bypass set. So for this particular car, it's on drive-by-wire because I have an electronic throttle. If you've got a throttle body which has got, say, an idle bypass, throttle bypass valve, then you would select this as throttle bypass and assign it in the I/O configuration to the output which you're using. You'll see that there's 2 outputs. That's because some throttle bypass valves have 2 solenoids on them, one for idle air up and one for down. So you would assign those, and then under the throttle bypass valve control, you can set the frequency to suit and the minimum duty and maximum, and you can also invert the duties for each of the outputs, so that basically if you were to apply 50%, it applies 50% in both directions for the valves, so that the air is being controlled well. You've also got a base fuel adder based on your bypass duty. If you've got a particular car which is, say, based on the fueling is done via throttle position and RPM, and you basically have a idle valve in there, if you increase the air from another source which is not reflective of the TPS, then you need to apply different fuel adders to it, which you can do in this particular table. The closed loop is basically the closed loop control of the idle control, and it has a few enable variables. Enable runtime, so after the engine is running up here we can click on runtime, so you can see it's been running for 8 minutes and 46 seconds. Enable vehicle speed, so once the vehicle speed is below this value it will turn the closed loop on. Enable engine speed error, so if you have a target of 1000 and the current RPM is, say, 2000, it won't be active until the RPM drops below 1800, because the RPM enable engine speed error is 800. Enable load select. This is basically your load. It would normally say, if you haven't got drive-by-wire, it would be TPS. That's normally the base thing you would use for idle control, but because this is drive-by-wire, our general driver demand for a load would be on PPS, so it's wise to use that. And you would select that too. And then you've got the enable load. So basically, when the value is greater than 1%, the idle control turns off. So if we click on the idle control, active is yes. If I increase the pedal position, you can see there that it's then no, and if I lift off the throttle, it goes to yes. So what are the other aspects under here? The base idle ignition adder basically allows it so when the closed loop has become enabled, you can actually apply an ignition retard or adder to suit based on temperature and runtime. This is quite useful in order to keep your ignition timing map to run a lot of timing in the lower areas so that the engine has a fair amount of torque there, but then when it comes into idle mode, it instantly pulls the timing out to reduce the engine's torque to maintain the idle better. Then you've got the breakpoints for error and derivative, and these are then useful for the proportional ignition control and duty control. So what these are is basically you have an idle error, so your target is say currently 770, and the actual RPM is 700. If I drag these two next to each other, you can put these in a tracer or as a gauge to overlay them if you want as well. You can go to a gauge and then overlay them, but just for the purposes of video, we're going to put them as a text. So what happens is your idle error is the difference between these two values, and you can actually plot that and view it in a data log, and you can see it jumping around here. So if I was to basically go into my base bypass duty and kick this up, for example, I'm just going to put mathad 1.5. You can see the idle error shoots up, and then what will happen is it will come down where the closed loop is adjusting to suit. And if I take this off, you'll see it dip down and then go there. Now what this is for is the proportional ignition control. Ignition is quite a useful aspect to control the engine torque and engine RPM, and you can see here that the timing of the engine will vary based on the RPM, idle error. Now the reason why it slopes down is because on the other variable here is the RPM DT. This is the delta change of the RPM. This is the rate in which the RPM is climbing or decelerating. So for example, if I was actually to plot that, and go RPM DTR as a trace, 50 Hertz. We're going to make this bigger so it's easier to see. So if I stamp on the throttle, and then as it decelerates, I should rescale this just to make it a bit easier to see. Let's make it 200 and 200. Okay, so if I was to stamp on the throttle, you'll see the RPM DT shoots up because the engine is accelerating rapidly. And then when you lift off the throttle, the RPM is decelerating, and hence the RPM DTR will come down and go negative. Now this is useful in this particular map and for the other maps because as the engine is decelerating if the engine is decelerating quickly, you need to slow it down, and that's why I actually have positive idle ignition values in here to slow the RPM down as it comes back into idle control, and the derivative is basically coming down with your idle error. So it's a nice way, and your shape of the map should generally look like that. Same goes for the duty map. So you can see here as the RPM, if you watch the live trace, if I rev it, as it comes down, you'll see that the RPM DTR comes down here. And if I basically chuck in some values in here, if I multiply that by say 1.5, add 50%, just increase that, sorry. What you'll see is that when basically the RPM DT is in that area now, if I plot the RPM, let's actually just do this a slightly different way. Let's go gauge RPM, trace 100 Hertz, and then make this resizable. And then add an item in here which would be useful to see. We're going to add idle error, and we're also going to add RPM DTR. So I'm going to change the colour of that RPM DTR so it's something that's easy to see. Put that to blue. Okay, so as we rev the engine, you can see there that the idle error comes down and the RPM DTR is adjusting to suit. So as you can see, the RPM DTR shoots up there, and then as it's coming down, if I press spacebar and go over that, let's just change that colour. It's just a bit difficult to actually see that blue. Let's change it to yellow. Nice. And then change the scale of the RPM DTR just to make it a bit easier to see. And spacebar to undo it. So we'll do the same thing again. You can see the RPM DTR does drop in this point here where the RPM is decelerating. You can see it's in negative numbers, and that's been helped generally due to the fact of this proportional duty adder. So basically I'm jacking open the throttle as it comes back down into idle to slow the engine speed down. If I was to actually put this at say -2 and do the same test, you'll generally find that the RPM, you'll see the RPM DTR is actually lower here because the engine is decelerating quicker, because the base bypass duty is not being, the throttle is not being added due to this proportional duty adder. So that's a useful map in order to better slow the RPM down, and you can do that even more wildly. We basically chuck in some more values here and then rev it. You'll see it slowly then coming down. You'll see the RPM DTR is a lot smoother, and the RPM you can actually see comes down and is really smooth in the way it comes down. Now those are quite wild values, but you can generally see the effect it has. If I undo those by pressing U and then do the same rev and look at the RPM difference, you'll see it drops a lot faster. So that's what that table is good for. And you can do that based on the integral term as well. And then you've got basically the proportional duty scalar when gear is not in neutral. Now what this is for is you generally, once the gear is applied and you're actually in gear and driving around, you don't always want to have such a wild Nishan proportional table and duty, because you've got the forces being applied from the gearbox as well, which can cause the car to go into shunting, etc. So I generally turn this down, the scaling, I half it generally when you're driving around to keep the car smooth when you lift off and come into idle, that you don't get any bucking and the Nishan timing or duty going back and forward where it's being applied against it. Integral duty enable, this is basically your I term for your idle control. This is the enable error for the threshold. And then you've got your gain table and the minimum and maximum. The decay is basically how fast the I term will be taken out. So we can actually just plot that and show exactly what's going on. So the integral term, basically if you look at your base bypass duty value here, it's 6.3 as we've set in the table. And then the integral here you can see is at -2.1. So basically in order, what it's doing, and if you look at the final, it's basically taking out 2.1% in order to get the drive-by-wire target to a point where it's maintaining the RPM target I've asked for. Now, if I was to rev the engine, you'll see the drive-by-wire target idle originally starts high based on the bypass duty and, say, the aircon duty that's been applied, and it slowly comes down based on the idle duty or integral term. So the integral is slowly taking out the throttle opening in order to maintain the target and bring the error down to 0. Now, the integral decay, basically your minimum maximum duty allows you to set a limit for the I term. So currently it's at 2 and 3. This is important so it doesn't wind up at all when you're if there are problems with the engine. But the decay function basically allows it to, when you were to say stamp on the throttle and come out of idle control, it's the rate in which the idle duty integral basically comes off. Okay, so if I was to set this at say 5, you'll see that the I term, where it's at 1.3, if I stamp on the throttle, it slowly decays out. If I was to set this at 100, wait for it to wind up again. If I set 100, as I come out of idle control, you'll see instantly it changes to 0. So that changes the decay and the idle control comes in and out, which is useful for basically any change in the RPM, any sudden changes in the RPM where the integral needs to basically be adjusted. You can slow that down in order to keep the RPM smoother. So some useful tips in order to get the RPM control nice. So the first thing, ensure your base bypass duty is close to what your actual TPS opening is. So you can see here the TPS opening is 5.4 and that's what's matching your your drive-by-wire target idle, and the base duty is at 6.3. So we could actually come into the base duty table and actually bring this down in order to get the integral term to be less and the drive-by-wire target idle and idle duty base to be similar, it basically allows all of the closed system to work easier and having to do so much adjustment. A reason why some people might want the base bypass duty 1 to be higher than the actual drive-by-wire target 1 target idle is so that basically as the engine is decelerating, the idle will be basically caught and then actually slowly brought down by the I term, a way to slow the engine RPM down. Let me just show you what I mean by that. So if I was to make this value lower, so the I term, so what you'll see now, when I rev the engine and come down, you actually see the RPM, it's pretty good, but let me make this lower. As it comes down, you'll see the RPM actually dips and then it slowly gets a hold of it. So if I just pause that here, you'll see the RPM here, look, it goes to 549 and then slowly corrects it to get it back to where we want it to be at 780. So the bypass duty, as you can see, has a huge effect on it. So if we bring this back up, now one useful aspect of this, if you were to make this higher like I've just made it now, when I was to do the same test, you'll see the RPM slowly decelerates and then actually basically pulls it back, so the integral term will then slowly start to wind up. So if you watch the integral term again, it basically the RPM will be higher than the target, catches it at 950 and then slowly pulls it down. Now another way you can do that to stop the actual base control having to work so hard is you can use some comp maps. So let's go over how that's done. So what we want to actually try to do is, like we do when the engine starts in the run mode, slowly bring the target down as you come back into idle control. So what we can do is we can go to View, Customize Options, and then go to Configurable Purpose Maps, 3D. And what we're going to do is in here we're going to make a CMU. So we're going to go into here and go Disconnect now. So we want to disconnect. So yes. And then what we want to do is we're going to do an idle target adder. And you can do an idle duty adder as well. So we're going to say yes, do we wish to proceed and tag? Yes. And then we're going to change the axis, one to be idle active time and the other one to be speed, or whichever you'd want. So speed's quite useful, so you can have a slightly higher idle target when you're moving around. So we set those, then we press V and then C again and come back to the configurable purpose maps. What we need to do is set the dimensions of the map, so 11, 12, and then change the breakpoints. So we're going to put in here, these look pretty decent, 0.05 all the way up to 3 seconds, yep, and then vehicle speed. Okay. So what you can actually see, you can actually see some values are in here from previously, but you can actually see as the idle active time basically increases, the idle comes down, the target idle comes down. Now what we can do is we'll save this. I'm just going to put there test 2, file close, device connect, get back into the ECU, just pop in the calibration password, file load, and then load this new map. Force engine stop because we have to program it because it's a vital change, and then under idle control you'll now see this new custom CM map. So what we'll do is zero out for the minute to show differences. Let's start the car back up. So what we can look at now, let's close this down and let's just look at our idle target, our idle active, and our idle active time, which is here. So what you can see the idle target is coming down at the moment because that's just based on the runtime. But what we want to do is actually slow the RPM down as we're coming back to a stop from revving the engine. So at the moment, if I was to rev the engine, you'll see as the idle control active comes in, you'll see that it just goes to yes, and the idle control basically pegs at 770. So if we were to open the RPM, put this in a trace, make it a bit bigger so it's obvious to see. Do the same test, you'll see here the RPM comes down. Now it's going higher than normal at the moment because of the base bypass duty, but if we were to take this down, so the integral is not having to work so hard, do the same test, see the RPM comes back down and then gets to its target a lot quicker. Now Let's say we want to slow the engine RPM down as we come back into idle. We can actually do this via this new CM map. So let's say we've got the idle target value here. The speed is currently 0. So if we make it 1,000, just as a wild jump for the minute, and then make that 1,000 all the way until it's 2 seconds, what we can then do is if we come back into idle, you can see the idle target now is 1,700, and then it slowly brings the RPM down. So obviously that's a wild step and change, but if you were to make it, say, less, what you can see now is the RPM will be caught at a slightly higher amount as the idle control comes out and it dips down. It works nice, you can see it there, the RPM slowly tapers down. It's a really nice way of doing it. Now in order to help the strategy, you can just make a custom map for the idle base bypass duty, same parameters, and it's a really useful way of getting it set up. Now just as one final add-on to the end of this video, since making this video we've actually done a firmware update to the S6, S7, S8 and S12 firmware to basically have some changes to the closed loop. Now let me explain these changes to basically allow users to understand why they were implemented. So the first one here that we have is the idle ignition authority ramp in time. Now on certain engines you generally need to have a large amount of ignition retard in the idle area in order to maintain a smooth engine speed and actually kill the engine's torque. The problem with this is that when you're entering and exiting idle and you have a lot of ignition timing in the low load area of your timing map, which generally will have like more timing in there than you would obviously need at idle in order to have lots of torque low down when driving, the problem you can have is when going between those stages of entering and exiting idle control, you can have quite a large jump in timing, which can make the car feel like it's kind of lurching or kind of dropping torque instantly, which can make it not smooth like we'd want for any road car-esque car. So what we've added is an idle ignition authority ramp in time and out time. The ramp in time is for when it's actually coming into idle control, and the ramp out is for when it's exiting. So let's just make an example of how that actually works. So for example, if I actually put in here, let's make it really long, 5, you can see the variable here, idle ignition authority, and then we can see here our idle add ignition add idle, sorry. So if I bring the RPM up, we can see at the moment there's no idle ignition timing being done via the idle control. As I basically lift off and it comes back into idle, okay, you can actually see the authority ramp up, and you can actually see the ignition timing ramp in as it comes into idle very smoothly. Now 5 seconds is probably a bit too extreme, 1 second or 2 would probably do, but also the reason we have an exit map is so that basically when you exit the idle control you actually generally want a lot of torque instantly, so sometimes you don't want to have a delay in the ignition timing. So generally the ramp out time you want that to be ½ second, and you should find then when you're driving around coming in and out of idle control as you're driving it will be very nice indeed. Now the other aspect is the enable engine speed basically obviously can go from 0 to 500 kilometers an hour. Now if you've got a particular car like I'm in the one at the moment, which is an automatic transmission or even a manual transmission with a clutch, to be honest, when you're driving around and you're above this enable engine speed, as you then say dump the clutch or put it into neutral, the idle control is not going to become active until it gets below this value. The problem with that is that basically because you've got another derivative of torque that's being applied to the engine when you are in gear, etc. If you were to set this high at say 500 kilometers an hour, and you lift off the accelerator while you're in gear, in third gear, and slowly coming to a stop, what will happen is you've got the opposing force of the gearbox being applied against the engine. So the idle control is trying to bring the idle down to say like 1,000 RPM, but obviously you've got the inertia of the car that's keeping the engine RPM higher. So what happens is the integral winds up, and basically when then you come back to a stop, you could have like say -2 or 3% integral reduction, and the engine can sometimes stall. So what we've done now is we've basically added a integral minimum maximum table, which is based on the drive ratio error. So when you start driving, your difference between your RPM and your speed works out something called drive ratio. And under sensors and gear, what you need to do is you need to drive along, okay, and actually enter these values for each particular gear. So when you're driving along, you'll see the variable drive ratio start to display some numbers, okay? And then what you can do is enter these numbers for each given gear into this area. What that does is that locks in the drive ratio calculation for each gear that the ECU would know, and enable the gear position from wheel speed if you want the gear position to be calculated this way if it's not coming in from an external source. On this particular car, it comes in from the transmission ECU, so we don't need to enable that. But what this does mean is that then you have the drive ratio error breakpoints. So basically, if, for example, you're stopped, your drive ratio error is going to be really high and your drive ratio is really high, okay? So what would actually happen when you start moving, what you actually find is that drive ratio error will slowly get closer to 0. And what that means is that basically you can see that there as I'm actually moving now. What we can actually do there is when we're in the 0 error positions or in the negative area, we can actually set that minimum and maximum at pretty much 0. So we don't want any integral at that given point. We only want the integral when the drive ratio error is high. So we can actually smooth that in between there. And then do the same thing here for the max. And what that means now is that the integral will basically be active when we're at idle. So you can see here our idle duty integral at the moment is adding 5% throttle opening. But when we start to move, if I actually show this now, as we start to move and the drive ratio gets closer to 0, what it will actually do is it will slowly then take that out. Now, I might not be able to get enough speed up where I'm here, but yeah, we can see there that the drive ratio error has gone into the negative where we started moving there, and then instantly the integral goes to 0. And then you can see as we come back to a stop, it then slowly winds up again. So it's a nice way of ensuring that you don't have any stored characteristics of using the enable engine speed, the enable vehicle speed at a high value. Hopefully this last update is going to really help to get your idle control dialed in perfectly.